Okay, so let's the second talk of this session. So this is also the last talk of this session. It's by Mei from the University of Denver. The title is Parking Functions, Multi-Shuffle and Asymptotic Phenomena.
Thank you very much for having me here. So it's such an eye-opening experience being at this conference. It's my first, but I hope to make more to this conference series. And I'm especially grateful to Bob for kindly introducing me to this wonderful community. Okay, so today I'm going to tell you something about parking functions. It's based on my most recent work on parking functions. And for background material, I will also reference an earlier work between me and Rick Kenyon. And for time reasons, I'm going to concentrate most of my time first on background and then on an original combinatorial construction, which we term parking function multi-shuffle. I'm going to give many examples and hopefully make every point clear. So if there is anything not clear, please feel free to stop me anytime. Okay. So let's get it started. What is a parking function? So the scenario is the following. We will consider that n people enter a parking lot, n cars enter a parking lot, and then they will each have a most preferred spot to park. And then if the spot is empty, the car will just park there. And then if the spot is already occupied, the car will just drive on until the car finds an available spot. It's a one-way parking street, so if towards the end of the street there is still no available spot, the car will just leave the street, and then such situation is not parking function. So we say the parking function of all the cars can move. This is a classical situation of parking function, and then there are many generalizations of this situation. We will consider one generalization with that. So for the parking function scenario, so how could I do example like we can? So I'm saying like the first two situations, all the cars will be able to park, and here I take n because n becomes 4, and then the last situation, the car will not be able to park because the first car will parking spot 2, second car will parking spot 3, but the car will parking spot 4, leaving the fourth car no available to park. And then parking function. So it has another. It was investigated by computer scientists also under different name called union probing with machine. So the scenario I just did here lots of words, but the idea is that there will be some items and they will try to store the item in a table. And then there will be a preferred spot where I store the item. And the spot is already taken and so on. And then we can say around. So the parking scenario described here is down to like a confined parking problem, where the last spot is left empty. And then the two different communities investigate the same problem with probably different language. So we usually say every time the n spot, and then when we are talking parking, we usually say n items and so n switch. And also it's confined machine, so usually the last spot is left empty. So that's my n horizontal and plus. But otherwise, it's the same one, which is the different language. And I'm going to make this all use the parking function. One of the more important things people are interested in is called exploration in parking function, and also the main like areas of users, cost of construction, and then money. So what it means is that I know a car will not necessarily park in its most preferred spot. And because the spot might already be taken by the previous car, so the car will drive on to some more to some other results later, and then there will be an impact on the distance travel. And then total displacement, their model is the total effect of the distance travel. And then linear programming information is the corresponding to the total effect of the excluding one zone in the table. Using teaching whole principle, you can see that there is an effective way to determine whether it is a function instead of trying to test it out whether it's part, or the functional part. Because if you think from the last cell or the last function part, you know you have the absolute scalar value of the part preferring the last cell. Because otherwise, the second part that prefers the last cell will have to be the key. And similarly, for the next two lines, we can have most of two parts preferring that. And then if you go backwards, you know in the whole principle can get an effective way to see whether it is a function function, which is in this point where one line equation. And that's true. And then there is an alternative way of using the technical principle, namely from a non-increasing rearrangement of Python functions. Then you see that the non-increasing rearrangement will be satisfied with I when less than in my interpretation. And from the technical principle and the non-increasing rearrangement, you can see that parking functions are independent from their combination. And I have a small picture here. So look at the tree here, showing you that the parking function. So we have the variant on the combination. So I just did the parking function like this. You'll see that the red dots represent this room. They represent rearrangement, and the black dots represent the technical principle. So this one corresponds to what we're showing us. This one is to essentially. Alright. So now let's review the definition in function function. So the basic is no way is involved here. So we do this. There's a most of that. So as phrase, it's introduced by the combinatorial and then many people have so many people have investigated this functions rather than perspective. We have problems, items, and people using the individual perspective, and also following Nelson, connected with identified model, and then generalizations, and then we also have some people in model, people have some and then from the probability and statistics perspective, people have also considered uniformly sum or uniform function, and what is the typical behavior. And then the way the probability work from earlier without the continuous probability from Alex and from Lincoln, they have very hard involved. So people have found that if there is a very significant distribution, then an area distribution when it's available, and then the Gaussian distribution of the table, and then the Poisson distribution and some other reasons, yeah, and I wanted to mention that some of the tables are not really typo versions, they are only typo versions. We have known without the and a lot more. So now let's consider a generalization of Python functions. So one generalization is for a new Python function, where new is that So it's an arbitrary vector. And then when we look at the vector in terms of strictly increasing order, so it could be possible that some entries have rich entity, or some entries are rich entity. That is like a small generalization to the twin transitive vector. So in this case, we are going to concentrate on strictly increasing activity. And then a real problem continues so that when we rearrange the partitions of the same also in non-discrete mode, and each corresponding entry is the rational entry we can do in a view. So we think that the current corresponding scenario is n partition and solve is actually the special situation of the view partition function. So you are in minus and plus. If you remember, the non-decreasing rearrangement condition from area. And then same as partition function with n partition and solve, view partition function can also have a Ramsey partition interpretation, where we think that the only way to solve towards the end of history. And then so here is the question that we are investigating in this talk. The question is, what we want to know, say, the first person could play such one, and then second person could play such two, or three, and then there are n people, n colleagues all together, and our n is very, very large. So we want to know how many such partition functions are there, or equivalently if we uniformly sample the partition function, well, n is very large, what the typical partition function will have. So to investigate this, because partition function is going to be symmetry, so we'll just write down all the results in terms of the first partition preferences, but remember the results can be introduced for very different things as well. So to introduce that, we will need to do a partition function multiplier. And before that, let's introduce this. So instead of 90 a bit bigger, if we're looking at it for the first time, because remember we are introducing the first answer for the C. Now we can fix the later frequency. So the idea is that because if you wanted to count how many partition functions are there once you fix the first frequency, it's quite difficult to count. So instead of directly counting that, we will do a back distinction and say that, okay, now if I also specify the later frequency, are they compatible with the first already specified frequency? And if they are compatible, then somehow increase the first frequency to a bigger value so that it still remains compatible. So it really is. So in it can conclude that if we fix the latest frequency, then the first frequency, which we call partition continuation, will have a maximum vector. And then because of the partition scheme, anything less than equal to this vector will also be a partition function. But we'll have an example. So here I'm saying that the U partition function, the U vector is given by 2, 3 times 8. And then I can really fix the third part to be fixed and the fourth part to be 2. So what I do is that I rearrange the frequency in increasing order. So in the 2 is 6. Then I find the minimum Gi so that it's greater than equal to the value. So for 2, the minimum Gi I find is 2, and for 6, the minimum Gi I find is 8. Okay. And then I see that the remaining Gi will be my V, and I just write my V in increasing order for the emissions. So this is how I got my V. And then it can be shown that if I know my third part prefers upstairs, fourth part prefers part two, then can parking preferencing of the first two parts, like one to three and five in component-wise partial order, where to be a partial function. But if you exclude 3 and 5, then they're not a partial function. So that is a partial function. Okay, even more words here. So let's look at an example of this. This is in the extent of it. So here is an example. So I know my new lecture is 3, 4, 5, 6, 7, 8, 9, 10. And then I know that I want to fix 2 preferences at 6 and 8. So here I have 6 and 8, and then 6 and 8 will break my partial function into 3 segments. So one is 3, 4, 5, and then the other is 7, and then it's 9 and 10. So I know that my partial function will be broken up into 3 segments. One is the real partial function of 3, 4, 5. And the other is the real partial function, but instead of looking at 7, I will subtract 6 from it, because that's how the segment is broken down. So then I see that the second segment is the partial function of 5. And then the last segment will be the one after 8, so 9 and 10. That's my vector. And I'm going to subtract 8 from it, so I get the new partial function, where the vector u is 1, 2. And then here, AofA1, AofA2, and AofA3 are just random normal types from this new partial function. And then a multi-shuffle means that I can commute all these numbers in any way I like. So here to make it more clear, when it's AofA1, it will keep the numbers as they are, and when it's AofA2, I will add the partial function 5, 6, because 6 was the number I subtracted in the previous step. And then for AofA3, I will add all components in AofA3 by 8, because that's the number I subtracted by. And now I get the then segment coming from AofA2 with that override segment coming from AofA3 with the underline. And similarly, let's go over the process one more time. So if I have u partial function, or u vector is 2, 4, 5, 6, 8, 12, and 15. And then my singularity that 4 and 8 are sum of multiplets. And then if we break down the partial function, again with 3 segments. One is 2, and then the other is 5, 6, and then the other is 12 and 13. And again, I do the same thing. The first component will be a u partial function. Well, if the vector u only has one symbol and 2. And then the second component will be a partial function. Well, the vector, instead of having 5 and 6, I need to subtract 4 from both countries. So here is the partial function. U partial function where u is 1, 2. And then the last one will be u partial function where u is 12 minus 8, which is 4, and then 15 minus 8 is 4. And then again, AofA1, AofA2, and AofA3, as this example I take from these u partial functions for illustration. And then I form a multi-example, meaning permutation anywhere I like. Except that AofA2, every entry in AofA2 needs to add 4 hash, and every entry in AofA3 needs to add 8 hash. So this is a multi-example. So let's look at the definition. So hopefully the definition, we don't need to worry. So we see that what we do is that we put selective reading, And the lecture image, there will be some elements from you. And then we want a parking function multi-level for elements that are multi-level, respectively. Namely, it will break down the parking function in as nodes out of one components. Some segments might be missing, and then the segments of the down junction with the parking function and the junction with the corresponding addition. So why I'm interested in this multi-level discussion? Because it can be proved that the way to count how many parking functions are there, where the maximum confusion for the last entry is used, exactly corresponds to a multi-level. So we're not going to do that with the 25. So let's look at an example to illustrate this. Remember in our previous slide, when we looked at the parking function multi-level here, let's continue with this example. So here we have our vector U, and then we have formed a multi-level of 6 and 8 in our first example and 4 page in our second example. So you can see that if I, so this was the multi-level example earlier. So from the multi-level example, we know how to find the maximal component somewhere. So we just perform the math equation rearrangement of the entry, and then we see which entries are missing. And then we look at the analysis, and then we see that this is 4. Right. So with this, actually we can do an explicit formula for the function we are interested in. For example, specifying the first parking preference, or actually specifying any L parking preferences, how many parking functions do we have? There are explicit formulas. So, for example, involving a child polynomials or other polynomials, that those formulas do not have closed form expressions. So we can do some simulating and then some approximations using the formula. But in that case, we have closed form expressions. So I'm going to give an example where the formula actually has a closed form expression, and then from an AD parking function. AD parking function, that means that with a zero vector, and the first view of U1 is equal to A, and then the I is an sequence. So the second view 2 is equal to A plus B, and then A plus 2B, and so on. So the vector of length N. And then AD parking function also generalizing the standard situation with N cars and spots. And there A is equal to N minus N plus 1. And then B is equal to 1. So for this, we actually have a formula saying that the number of such parking functions is equal to A times A plus N to N minus 1. And then it generalizes the N parking with N parts and N spots. And then we are going to do some simulation. Well, it's when we share acting products. So P is greater than 0 and equal to 0. So P equal to 0 will correspond to N parts and N spots. And then C greater than 0 will correspond to a situation where one fewer parts than the number of spots. So the simulation we draw is suggested by this algorithm, can be by 7. So this algorithm is saying that we will choose a random element, and then we will add K times 1, so assuming what this corresponds to is that you traverse the car through a circle. And look how that can be what it's related to circle archery in counting calculation. And then we will just choose something uniformly and then here I have a simulation picture. So this simulation picture is the distribution of the weighted parking preference between the different scenarios. You can see the pictures don't look exactly like for C equation and zero C equation. So there are more simulations into that. And then remember as a parking communication symmetry, it also represents the parking preference distribution of any class, not necessarily the first class. And here I have a formula. The formula is for any number of cars and any number in power. So if any means the moment parking preference and expectation. But here I did the extension up to this order, but it could be done up to any order. It's just a formula to calculate that. And then in order to do that, we will utilize the tree function. And actually, it's a multi-dimensional product of the tree function. Yeah, we've already developed a algorithm. So, next we'll see a formula. The second looks like this. So this is the situation when C is equal to 0, and then we can see there is free space shaking in the correction term. So what is greater than 0, the space of correction term is all the ground and so therefore C equal to 0 and the space correction term is all the ground over the. So that's a big jump in the space correction term. And also the tree function does not work in this case because tree function is related to that of W function. So it only works when we make the W related when it's less than 1, somehow other function. So there is a convergence related to tree function. So for this scenario, we use a multidimensional able theorem. And then in earlier parts, able binomial theorem was mentioned, but here we also have to go to multi-dimension because we are considering arbitrary number of cars. And multi-dimensional able theorem could be used to investigate this situation as well. But then the formula is not be as nice because because whereas the calculation able multi-dimensional actually involves a lot of things. So I have to rely on computer algebra on So and lastly, I will just show one more simulation picture. With a simulation picture of the purple car under the different scenarios. And we see that they still look exactly like okay? So one approach is a Gaussian distribution, the other approach is an area distribution. And the regime under consideration in this paper is when M and N linearly depends on each other linearly. And then we're considering like expectation values and so on. But I now say in one paper, we consider M and N depends on each other in a square root way, and then we consider total loss, but not expectation. So there are many unpacked areas here. Lastly, I just wanted to say it's only a small step, but on a long journey in country more than anyone. Thank you.
One question. Yeah.
Okay.
So this last simulation results only, or you had a proof of them?
For some of them we have a proof, but not all of them.
Oh,
Mm-hmm.
which techniques are you using to get the distribution results? Testing one test method, or are you using other technology?
Oh, yeah, that's a very good question. Thank you. So, to get the distribution results, we first map it to true. So, I mean, if it's expectation results, we can just use tree function method and multinomial theorem to do the calculation. But like if you want, say, conversions to Brownian motion and stuff, then we first need to map it to a tree or forest, more general situation, and then start working in forest, and then using random walk, which is Poissonian distribution, and then using the correspondence to show the convergence to Brownian motion.
Thank you.
Any other questions? If not, then that's it. Thank you. Just from